I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
the brain, life,
The universe.
This week, what will your house look like in 2050? We're examining how new developments in science are informing the way we'll be living mid-century.
Plus, news of how painkillers can actually make pain worse, how the Earth came by its magnetic field, and a maths prize for solving a 350-year-old problem. I'm Connie Allbeck.
And I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, could painkillers actually make pain worse? Opioid drugs like morphine and codeine are extremely powerful and they're very widely used. But new research shows that they quite literally have a nasty sting in the tail because they appear to cause chronic pain in their own right. Peter Grace is at the University of Colorado, Boulder.
So the opioids do work exceptionally well for acute pain when they're initially being administered. Their effect actually diminishes over time, so it means you need to take more drug to get the same pain relief. What we're also showing now is that over a longer period of time, the effect not only wears off, but they actually start to paradoxically induce pain in their own right.
So what did you actually do and how did you stumble on this discovery?
We did an initial study where we looked at rats, we gave them a peripheral nerve injury, and then waited 10 days and then gave them morphine for a 5-day period. Once that morphine treatment had concluded, we looked at their pain levels and we saw that those rats that had received the injury but no morphine recovered after about 4 to 5 weeks. But those rats that had received morphine for just that 5-day period took double the time to recover. Their pain only resolved 10 or 11 weeks afterwards.
So what you're saying is that they continue to show a heightened evidence of being in pain for twice as long if they'd had morphine than animals that didn't have any morphine.
That's exactly right. So we're looking at the sensitivity of the rat's paws to touch. A normal healthy rat will just feel a tickle on the paw that won't bother them. A rat that is in pain will violently withdraw their paw.
How did you pursue that then, Peter? So you have these animals which, if they've been given painkillers, paradoxically seem to then experience more pain for twice as long as if they haven't had opioid painkillers. How did you investigate what was actually causing that?
Our first port of call was looking at these immune cells in the spinal cord called glial cells. They're there to surround and support neurons. But what we've shown is that these cells are really sensitive to any sort of injury or foreign substance. So these cells are activated. That means they start producing these inflammatory mediators that activate pain-sensing neurons, and they're activated after peripheral nerve injury, but they're also activated by morphine, and that then leads to these paradoxical effects on pain.
So you injure the nerve, and that winds up these glial cells, and they start to become more active. At the same time, you give morphine to quench the pain that you're experiencing, but that also winds up these glial cells and makes them even more active. How then do you end up with the chronic pain, this pain that relentlessly goes on even after the original injury has subsided? How does that get entrenched?
Yes, the combined challenge of the peripheral nerve injury and the morphine sends these glial cells into overdrive. So they're far more reactive and they're spewing out far more of these inflammatory signals with the combined challenge than had either one of them, the opioids or the peripheral nerve injury, in isolation. So because this immune response is so great, it leads to perhaps some extracell damage in the spinal cord, as well as enhanced signaling at these pain-sensing neurons.
Could a person therefore end up in a sort of feedback loop where they initially have an injury, they get given opioids because they had severe pain and they needed to control it, but the damage to their nervous system coupled with the exposure to the opioid drug means that they then end up with pain produced by having taken the opioid. So they then take even more opioid to control the pain, and it just feeds back on itself and they end up in this loop they can't get out of.
Yeah, that's exactly right. And that's precisely what our study suggests. importantly, I think that the silver lining here is that that cycle can be broken if the immune system, specifically within the spinal cord, is blocked. And we've been able to do that in our rat study here. And we're currently focused on developing a couple of drugs that will hopefully get out to patients to help break that cycle.
So what would your advice be then to someone who has an injury? Should they not take the morphine if they can avoid it or minimise their exposure? What's the best way not to end up with one of these chronic pain states?
Opioids really aren't a long-term solution for chronic pain. I think that for an initial acute injury, they're fantastic, and they do an excellent job at managing that pain. But if the pain starts to persist, I think it's best to have a conversation with your doctor to see whether there are any other alternatives that might work for you. And there are some other drugs out there that are really excellent for chronic pain.
That was Dr. Peter Grace talking about his work, which came out this week in the journal PNAS. That's the Proceedings of the National Academy of Sciences, USA.
The Earth's magnetic field is essential to life on our planet. It shields us from the harsh conditions of space. The field is produced, we think, by the constant circulation of the Earth's metallic liquid iron core. But how long the iron core has been flowing, and therefore the age of the planet's magnetic field, have been open questions that have led to a paradox, which Stuart McWilliams thinks he can now solve.
The paradox, it was proposed a couple years ago, or really, it was clarified a couple years ago. And that is that when you have very high thermal conductivity in the Earth's core and of iron at these conditions, it's very hard to sustain the Earth's magnetic field. The heat is removed out of the core relatively quickly, and there's not enough energy left to support the vigorous kind of motion that produces the Earth's magnetic field.
So this paradox lays out a problem. We have a highly conducting molten core of iron. But if it's highly conducting, then either, 1, the Earth's magnetic field couldn't have been around for that long. It would have burnt itself out, and we have rocks that date back almost to the beginning of the Earth, showing its presence. Or 2, early Earth must have had a super hot molten core in order to retain the heat for as long as it has. But that doesn't really work either, as we know the Earth has remained largely the same. So what's going on? Well, it all hinges on this question. What are the properties of iron in a super hot, pressured environment like the centre of the Earth?
We take two diamonds, similar to those in a diamond ring, but if you take it out of the ring, you'll notice there's a really pointy part at one side. And we essentially take those 2 points of two of those diamonds and press them together, in this case, on a piece of iron, and we squeeze down as hard as we can on this iron, and we can create the same kind of force that's on iron in the center of the Earth. Of course, the center of the Earth is also very hot, so of course the iron in the center of the Earth is partially liquid because it's so hot and it's melted, and so to get to those conditions, we have to heat it up. And this is where the diamond is also very helpful, so it's very strong. That helps us squeeze on it. It's also transparent, so we can see through it. Or we can, in this case, shoot a laser through it, and that heats up this little piece of iron to many thousands of degrees. And so we create, by squeezing on the sample and heating it up with lasers, we create those conditions in the center of the Earth.
And from that, what are you trying to find out?
We've been able to get to these conditions with this technique for a long time, but what we're trying to find out is something very specific and something that's really hard to measure. That is how well the iron will conduct heat at those conditions. This is really important for establishing properties of the Earth's magnetic field, how long it's lived, and so on. And so to measure how the heat is transported at these conditions, we have a little tiny piece of iron between these two diamonds that, if we heat it on one side with a laser pulse, then the heat will slowly transport itself across this hair's width sample, and we can measure it come out the other side. I say slowly, it happens on the time scale of a few nanoseconds, so we have to make the measurements very quickly. But if we can measure how fast this heat goes, we can determine how the heat also flows inside the center of the Earth.
So this is where you came in trying to recreate the center of the Earth to see how well this conduction happens. And what did you find?
So for these very high thermal conductivities that we expected for iron, the Earth's magnetic field might only be very young. It may not have been around very long, and it might also have a very short lifespan into the future. We find that, surprisingly, the thermal conductivity is very low, unusually low for metals. And what this means is that the Earth's magnetic field can, in fact, be very long-lived. In fact, it might have been around since the very formation of the Earth, even before the first life on Earth, which is really important implications for the spread and evolution of life.
An attractive piece of research. That was Edinburgh University's Stuart McWilliams. His paper describing those findings was published this week in Nature.
You're listening to The Naked Scientist with me, Chris Smith, and with Connie Orbach. Coming up later, we're in Oslo for a maths prize for solving a 350-year-old problem. And what is your home going to look like in 2050? We're exploring the houses of tomorrow.
But now it's myth conception time, and this week Kat Arney has been living up to our naked theme and exposing the truth about the weird and wonderful naked mole rat, which is said never to succumb to cancer.
Often described as wrinkly sausages with teeth, the unattractive appearance of naked mole rats masks their unusual biological properties. Pink and hairless, these extraordinarily long-lived rodents live pretty much their entire lives in the dark underground, up to an impressive 30 years, in groups with similar social structures to insects such as ants and bees. Unusually, they can't feel pain, as they have no pain receptors in their skin, and unlike other mammals, they can adjust their body heat to match the temperature of the outside world. But Heterocephalus glaber, to use the naked mole rat's Latin name, is most famous for a health-related trait. They never get cancer. Recent studies revealed that the cells of naked mole rats make a sticky substance called hyaluronan, which is thought to stop tumours in their tracks. And genetic studies have revealed that the animals carry exceptionally potent versions of genes known as tumour suppressors, which stop cells growing out of control and forming cancers. In 2013, the journal Science even named the naked mole rat Vertebrate of the Year, thanks to their amazing cancer resistance. But in 2016, 2 papers turned up showing that this unbelievable ability is just that, unbelievable. Looking at 37 naked mole rats that had died between 1998 and 2015, vets at Disney's Animal Kingdom in Florida discovered 4 cases of cancer in the animals. One with liver cancer, another with a kidney tumour, a third with a type of cancer called lymphosarcoma, and another with what looked like esophageal cancer. Researchers from the University of Washington also announced they'd found 2 naked mole rats with cancer. One with a tumour that probably started in its salivary gland, and another with a type of stomach cancer known as a neuroendocrine carcinoma. The first one is still alive and living in a zoo in Illinois, but the second one died, probably as a result of the disease. Proving that it's always risky to say something never happens in science, these discoveries show that although it's still very rare for naked mole rats to get cancer, it can still happen. Even so, their unusual longevity and low, but still real, incidence of cancer makes them interesting animals to study to find out more about what's going on and see if we can get any clues about our own human lifespan and cancer risk. And they aren't the only members of the animal kingdom to be rumoured to have inbuilt cancer resistance. Right at the start of this series, I busted the myth that sharks don't get cancer. They do. And elephants also have unusually low rates of tumours. Yet, they have many more cells than we do and live just as long, something known as Peto's paradox, after the great scientist Richard Peto. Just last year, Josh Schiffman, a children's cancer doctor in Utah, discovered why. By gathering samples of blood from the elephants at Utah's Hogle Zoo, he discovered that these enormous pachyderms have extra copies of a tumour suppressor gene called P53, known as the guardian of the genome, that helps to stop cells turning cancerous when they damage their DNA. But they're still not completely immune to the disease. Sadly for sharks, elephants, and those wrinkly naked mole rats, like the superpowers of comic book heroes, the idea that they're completely invincible, at least to cancer, is just as fictional.
Kat Arney. And if you have any suspicious-sounding science that you would like Kat to demystify for you, you can send it in. Email chris@thenakedscientist.com. You can tweet @nakedscientists, or you can find us on our Facebook page, and we'll take a look.
A few years ago, the news wires were buzzing when researchers showed that flowers attract bumblebees using electrical signals, and that the bees can tell one bloom from another just on the basis of flower power. But how do the bees do it? Emma Sackville caught up with Gregory Sutton, who's recently found out.
Bumblebees are magnificently fuzzy. And this fuzz gives bumblebees a sensory ability to tell things about the world around them. It's not just for keeping them warm, and it's not just for measuring wind currents. It's also for measuring the electric fields of various plants and animals around them.
And how did you go about testing these hairs on the bees?
So there's 2 experiments we ran. The first is we put a hair in an electric field and used a device called a laser vibrometer to measure the hair's motion in the electric field. And we found that when you change an electric field, the hair moves back and forth, and you can actually oscillate a hair using an electric field. And then the second experiment is you put a hair in an electric field, and we were able to get very, very fine wires placed at the base of a hair. And those fine wires would tell us what the cells and other structures at the bottom of the hair were doing, and you record the electrical activity in the nervous system to see if the motion of the hair causes an electrical signal to be sent back to the nervous system.
You mentioned that bees can detect these small electrical fields. What are the implications of this? If they can detect flowers, can they detect other electric fields?
We don't see any reason why not. We found that they can tell the difference between different flowers, and we're currently working toward defining exactly the kind of electric fields that they can detect and what electric fields affect them and what electric fields don't.
So could electric fields that we produce cause any effect to them?
That is a very careful question, and I'm not comfortable answering that. Any answer I give to that question will make somebody angry. So I'm not comfortable answering that question until I have data that says specifically one way or the other.
Sure, okay. Bees can detect these fields because they're fuzzy. Are a lot of other insects similarly fuzzy?
There are many, many insects and spiders that are fuzzy. There are fuzzy moths and fuzzy butterflies. There's a couple fuzzy crickets. The abdomen of a lot of spiders are fuzzy, which makes us suspect that there are many, many insects measuring electric fields in this way.
And what would other insects use the electric fields for?
Well, the easiest thing is that we found that insects are actually electrically charged, and they create their own electric fields. And if you had something that sensed electric fields, you would be able to detect the presence of another insect nearby. This would be no further than, say, 10 or 20 centimeters, but it would be a close way to tell if there were other insects nearby. And because many insects eat other insects, this would be of great, great utility to all sorts of insects if they could do it.
Why is it important for us to know how bees detect flowers?
So in the pure scientific sense, everything that's known between bees and flowers is important for just agriculture and fruit. There are many, many fruits pollinated by bees. If we know how flowers and bees interact, we can actually create farms that are more friendly to bees and increase pollination levels. From a larger sense, this is a branching into a field of electrostatic biology, which, if we find this in many, many other insects, might be a whole realm of interactions that we might need to know in order to control or otherwise affect insects. And this was not the first paper over the last couple of years to show that the insects we deal with every day are doing amazing things, and this will by no means be the last. And we know so little about what's going on in the insect world of the guys we encounter just in the park and just in the garden and just on your windowsill. And that whole area of science, I think, is fascinating, and it tells us about the world we live in. It's the things we see every day.
Gregory Sutton from the University of Bristol. He was speaking with Emma Sackville, and he published that work in PNAS, the Proceedings of the National Academy of Sciences, USA, this week. To maths now, and last week one of the world's leading mathematics awards, the Arbel Prize, was given to Oxford University's Andrew Wiles for solving the 350-year-old puzzle posed by the French lawyer and mathematician Pierre de la Fermat. Our reporter, Timothy Ravel, was at the ceremony in Oslo, Norway, to soak up the mathmosphere.
Did you know there's no Nobel Prize for mathematics? Well, every mathematician does, and they're pretty sure they know why.
Nobel's wife ran off with the mathematician.
Nobel's wife had an affair with a mathematician?
I heard this story from so many different sources while studying for my degree in maths that I was convinced that it just had to be true. But when I looked it up, it turned out that Nobel didn't even have a wife.
The truth is, Nobel just wasn't really interested in mathematics. He didn't believe, as he should have done, that mathematics was a fundamentally important field for mankind.
which means in maths, instead of the Nobel Prize, there's the Abel Prize, named after the Norwegian 19th century mathematician Niels Heinrich Abel, which was awarded last week.
As the president of the Norwegian Academy of Science and Letters, it's my pleasure and privilege to announce the winner of the Abel Prize 2016, till Sir Andrew Wiles.
Last week, some of the greatest mathematicians from around the world gathered in Oslo to celebrate this year's Abel Prize winner. There was a serious buzz, the champagne flowed, and even the Norwegian Crown Prince attended. And whilst I was there, I bumped into author Simon Singh to find out why Sir Andrew Wiles was getting this year's prize.
350 years ago, Pierre de Fermat said he could prove that this equation had no solutions, but he never told us what that proof was. It's like having a buried treasure. Somebody says they buried the treasure somewhere, but they're not telling you where the treasure is. And so every other mathematician in the world has been treasure hunting, has been looking for this proof, trying to rediscover what Fermat said he had all those centuries ago.
Pierre de Fermat was a French mathematician who in the 17th century was working through his favourite maths book, when he started to think about square numbers and how to split them up. 25 is a square number, he thought, because it's 5 times 5, but 25 can also be split up into two smaller square numbers, 16, which is 4 squared, and 9, which is 3 squared, which when added together give back 25. Carrying on this thought, Fermat wondered if cube numbers could be split into 2 cubes, or fourth powers split into 2 other fourth powers, but he could never find an example. Instead, he declared that for anything higher than squares, this type of number split was impossible. But then, he died, and his proof was never found and proved pretty difficult to reconstruct.
Every century, mathematicians tried to prove Fermat's last theorem, and every century they failed. And the more they failed, the more of a precious problem this became. But still, nobody could find a proof until Andrew Wiles came along. He was one of the few people in the world who had the audacity to think he could even try to prove Fermat's last theorem.
I'm Andrew Wiles. I'm a professor at Oxford, the Royal Society Research Professor. So when I was a 10-year-old, I was visiting a public library in Cambridge and just rummaging along the math shelf, and I came across this book by E.T. Bell, and on the cover it described this problem, and so I spent my teenage years trying to solve it, and actually had to stop myself when I became a professional mathematician and realized that the methods available at that time had really got nowhere for 100 years, so it would have been rather arrogant to devote too much time to it as a professional mathematician.
But then, the game changed. Mathematicians proved that there was a completely new way to tackle Fermat's last theorem by connecting it to another completely different, unsolved problem. The new mathematics said that anyone that could solve this new problem would solve Fermat's last theorem as well.
The moment I heard about that, I remember exactly where I was having tea somewhere, and someone told me about this, and I was in shock, and immediately I started working on the problem. I believed I could solve it, but possibly not in my lifetime.
Wiles then withdrew from the mathematical community, opting to work secretly, completely alone for over 7 years, toiling away until he eventually solved Fermat's last theorem, once and for all. He felt elated, but also a certain sense of sadness for his mathematical quest being over.
I have to say there's a tiny feeling of losing something. It's been a very private enterprise, and once you share it with the world, you're sharing it. And it had been my non-stop companion for years by this point, and now I was passing it on.
Once Wiles shared his proof with the world, he shot to fame and was even offered a modelling contract as well as having a musical written about him. Not bad for just proving a theorem. Wiles has received a lot of prizes for his mathematics over the years, and now he can add an Abel Prize to his trophy cabinet as well.
It is a pleasure to express my deep gratitude to the Norwegian Academy of Science and Letters and to the Abel Committee for awarding me this prize. Thank you.
That was Timothy Ravel reporting from Oslo.
Hello,
Greer here from Naked Astronomy. I wanted to say hey and tell you about my new podcast. It's an awesome audio adventure into the big black cosmos that we inhabit. What's out there? How did it all begin? And what will happen in the end? Presented and produced by yours truly. You can find it on most podcasting platforms. Just search Naked Astronomy.
This is The Naked Scientist with me, Chris Smith, and with Connie Orbach. If you'd like to get in touch with the programme, it's chris@thenakedscientist.com. You can also find us on Twitter @NakedScientists. On to the main theme of the show this week now, and we're asking, what will your home look like in 2050?
With a growing global population, we're facing a considerable housing shortage, both in terms of numbers of houses and the quality of that housing. In fact, a 2014 report by the McKinsey Global Institute, or MGI, estimates that by 2025, 440 million urban households, or as many as 1.6 billion individuals worldwide, will face crowded, substandard housing. So we need to build more homes.
But in countries like the UK, about half of the population's carbon emissions come just from the buildings we inhabit. And to meet the demands of climate change obligations, we need to cut those emissions by 80%.
So, can we have sustainable housing that still meets the demands of a growing population?
Well, let's build from the bottom up and look at how we can lay the foundations for more sustainable housing. Making concrete accounts for 5% of global carbon emissions. So is there a better alternative? Well, Darshil Shah is an engineer at Cambridge University and he works on construction materials. What, Darshil, is so attractive about concrete and steel in construction that means we use it all the time?
Well, there is a founded industry on steel already, and also steel has high strength and stiffness, therefore load-bearing capacity, and you can form it into complex shapes, and that enables load transfer efficiently. I think one of the advantages of concrete is that the material is available abundantly in many places, and that you can form it into different shapes of all sizes. Yeah.
So it is a good material, but it's not as good as a natural material, potentially.
Yes, in different ways, though. The three mainstream construction materials are concrete, steel, and timber. So, for example, up to 25% of new homes in the UK are based on light frame timber. And the advantage of timber in this respect is that it is a carbon sink.
Because it's soaking up carbon dioxide from the atmosphere to turn it into wood in the tree.
Yep. The production process itself can be carbon neutral if you employ a closed loop cycle where the fuel is generated through the offcuts of the wood that is produced.
Well, that's why I asked you about natural materials, because on the one hand, if we were to build buildings with wood, that sounds good because they're going to soak up CO2 from the atmosphere. They will be a strong material that we know from thousands of years of construction appears to work. But how quickly do we need to renew buildings made of wood? Because there's obviously going to be an energy cost in building the building. Mm-hmm. Building it with wood sounds good, but then if I have to do it every 20 years, not so good. So how does the maths and the sort of equation balance?
So the design life that we tend to work is between 50 to 100 years. And that matches quite well with the harvest cycle or the rotation cycle of timber. So once you have a new harvest, once you have a new set of wood, you can create new homes and replace the existing one.
Now, one of the projects you're working on is to look at or explore the possibility of using GM wood or bamboo in order to better serve the requirements of architects and engineers. Tell us about that.
I think we first need to understand wood as a material. We are looking at the cellular level through plants like Arabidopsis thaliana, which are the mice of the plant world whose genetic sequence is well known, and our host biochemists, Professor Paul Dupree's group, is able to modify these plants and change this polysaccharide constituents of the cell wall and the microstructural conformation of the stem. And the interesting thing is that the wood formation in these tiny little stems, 1 millimeter in diameter or even smaller, is similar to that in hardwoods, in poplar, for example. And therefore, by studying these genetically modified stems and looking at how maybe a small change in the xylan content or the cellulose content and how the interaction between the polysaccharide changes affects the properties of the material. And therefore, we can then work our way towards genetically modified poplar and better understand how the properties of wood come about and what we can do perhaps to improve the properties of wood.
Right, so we have this project here where you're actually going from the cell right up to the mature plant, organism, tree, whatever. So you can actually potentially generate a tree that will generate the wood which will have the properties that you need for a certain building project. I mean, is that what you're doing?
In a way, yes. And I think that's an important point because trees, how we use it, well, trees weren't made to be used in a dry state. In nature, trees are quite wet and it's not really a building material, and we are using it as a building material. So if we want to use it as such, we may have to engineer it for those properties.
Right, so because we dry the wood out to turn it into a plank, it then loses some of the naturally evolved properties it had as wet wood.
Yes.
Are you there? Have you solved the problem? Are you getting close?
It's not only a multi-scale project from the cellular level to the building level and even to the city level, but it's also, this work is at a fundamental level. So we are still trying to understand at the cell wall scale how the properties are derived. And at the other extreme, we are trying to understand or trying to develop concepts and products that can be actually implemented for the designs of actual buildings. You have to keep in mind that there's a life cycle in growing a tree, and it's only after 50 years or so you'll be able to harvest that tree. So you have to do a lot of long-term planning with these sort of projects, and we are, I think, a long way away from it, but it's a strong start in the right direction.
In other words, you can make sure that what you plant to be the sustainable wood source of the future, because at the end of the day, we want to reassure people here, you're not talking about going out to the nearest forest, chopping down a whole load of trees, getting wood and turning those into houses. You're talking about let's have sustainable wood supplies, but let's plant something now with 50 years hence in mind, which is going to be actually fit for purpose.
Yes, absolutely. Deforestation is still a problem, although deforestation rates have been reducing. And importantly for us, substantial amounts of wood can be harvested sustainably without depleting or degrading forests. And since the 1990s, on average, Asia and the developed countries, so North America, Oceania, Europe, have extracted about 3.8 billion meters cubed of wood annually, and yet forest cover has increased annually by 1 million hectares. So you can extract wood resources efficiently and sustainably.
Now, given that the McKinsey report we referred to earlier said that there is this very pressing need just by 2025 of, 440 million households in really quite poor conditions or needing better quality housing. Are you going to get there with this work fast enough, taking into account it's going to take 50 years to grow this sustainable timber source?
By 2050, we will have an additional 30% of wood resources, just new growth resources to use. So it is possible, it will be hard, but if we think carefully about it and think about how we are actually designing homes, because using timber, we will have to think about redesigning them using these new materials rather than basing designs for steel construction or concrete construction. So the efficient use of resources is the key over here. And like in the energy industry, you want a diverse mix of energies, you would want to use a diverse mix of materials efficiently.
And I suppose if it does need a bit of DIY, then you could always grow the raw material in the garden, couldn't you? Thank you very much. That's Darshil Shah, who's an engineer from the University of Cambridge.
Although the materials our homes are built from might be taking inspiration from the past, the way we power them certainly isn't. Solar power, known as photovoltaics or PV, is showing enormous promise, as I heard from Oxford University's Professor Henry Snaith.
Most solar panels are made out of a material called silicon, which is a semiconductor. It's the same material we use in our computers. It absorbs sunlight, and from that sunlight it generates electricity. The silicon was quite expensive, but it's been scaled industrially over the last 10 years especially, and now it's actually not very expensive. This means that solar power is almost as inexpensive to make electricity as conventional power, like coal and gas. And of course, this depends on where in the world you are and how much sunlight you have.
That's quite surprising. I didn't realise we were quite as close as that. But they're not ideal yet, are they? Because they're not particularly efficient.
No, well, I guess it depends on what scale you look. But the efficiency of a module, we sort of measure it as an efficiency of converting solar energy into electrical energy. And they're typically around 20%. And that probably sounds, that's not very efficient. You've got 80% left that you could get. But actually 20% is still quite good, but we can do better. There is a way of making solar cells more efficient, and that's a type of device called a multi-junction device.
Silicon is a single-junction device, meaning it only absorbs certain parts of the sun's energy. But if you have lots of different junctions in the solar cells, each one can collect a different part of the light, like ultraviolet or infrared, therefore increasing the amount of sunlight you can make use of. In fact, for a multi-junction device, we could get up to 50% efficiency.
Fortuitously, a few years ago, about 4 years ago, we discovered that a new family of materials called perovskites could work very, very well in solar cells. And these materials are based on salts that mix together and form a crystalline compound, very similar to, for instance, just salt, table salt, that dissolves in water. When it dries, it crystallizes to form little crystals. And it appears to have all the good properties of these very high-quality semiconductors, despite being very easy to process.
Well, that sounds great. Why are we still messing around with these old-fashioned ones then? What's going on?
Okay, all new technologies take a fairly long time to work through all the problems to get them to fulfill their promise. So, as I said, we sort of discovered these perovskites worked well about 4 years ago, and since then there's been an absolute explosion in research interest. There's been increasing commercial development in getting these technologies to the level that they can outperform current technologies and then enter the market. So we want to be able to do it within the next 2 to 5 years. But there are a number of challenges that still remain. The promise is all there, but we have to deliver now by making sure these materials and the solar cells will last for 25 years, making sure they outperform silicon not just on small cells, but also on large areas, mass-produced every day. All the modules have to be at very high efficiency. There's also a drive towards being able to make these solar cells look like glazing, so that you can have tinted windows and be able to generate a fair amount of power off them while also being able to see through.
And can perovskites deal with that?
Perovskites can be coated directly onto glass, so you can make what we call a thin film module. So perovskites can basically look like a sheet of glazing.
Thinking about timescale, what are we thinking for our house in 2050? Is it going to be powered off solar?
It has every possibility of being powered off solar. The technology will definitely be there to do that. The balance is really the cost differential between producing your electricity in a field and then just using conventional transmission to transmit the power to the building versus the benefit of producing the power locally on the building. And combining that with the aesthetics, the stuff to really make a big impact on buildings, it has to be versatile, because architects are rather pernickety about what a building looks like. Maybe fortunately or unfortunately, exactly. So we have to develop technologies that are versatile. And then I think we will see a situation in the future where any free space which is exposed to sunlight will be generating power.
And in terms of price, we're expecting that to come down a lot as well?
If I had to make a prediction, I'd say in 15 years' time, probably PV anywhere in the world with storage will be cheaper than any other technology for producing power.
So in 30 years' time, Chris, you can invite me around for dinner in your new solar cell windowed wooden house. That was Henry Snaith from Oxford University.
Well, I very much look forward to that, Connie. You're listening to The Naked Scientists with me, Chris Smith, and also with Connie Orbach. Still to come, would you share your washing machine with your neighbours to make life more sustainable? We'll find out. Plus, how do noise-cancelling headphones actually work? First, let's look into what's being done now to build environmentally sympathetic homes. In a number of countries, proposals that from 2016 new buildings should be sustainable have been watered down or scrapped. But one development in Cambridge is sticking to its guns anyway, and Emma Sackville went on site to speak to construction director Gavin Heapy.
We are recycling water We are generating our electricity and heat through our energy centre, which centralises the production of electricity and hot water across the whole of the development for all 3,000 homes. We're generating electricity through photovoltaic cells, but what we're also doing to achieve that is ensuring that we reduce our carbon footprint both in the construction of the homes, but also in the materials and also the performance of the homes when they're in full use.
And we've got this energy centre behind us, is that right? So it's a sort of tall grey building. How's it going to function?
So within that building there are different ways of both generating electricity and heat. In the initial phases where the whole project is very much heat-led, so we've got more demand on heat rather than the electricity, we use boilers. So the centralised boilers then pump hot water around the development, and then as the development requires more in the way of electricity, we'll start generating electricity with engines.
This system is known as Combined Heat and Power, or CHP, and by centralising the boilers, not only do they make it more efficient over the whole site, they can also use the waste heat from the engines to power the boilers, and Gavin reckons it could all add up to an overall energy saving of up to 40%. Building on this kind of level is quite a big ask. What have been your main challenges and stumbling blocks when you've been trying to achieve it?
The main stumbling blocks have been to do with finding the best people to deliver these projects. Not everybody has done anything at this scale before. So finding the right resources, both in terms of the management team, but also the contractors and their subcontractors as well. And also making sure that we keep a close eye on how that performance is working on site.
And obviously there's a higher cost associated with building something sustainably. How are you balancing off the cost with the trade-off of making a sustainable housing?
Well, ultimately, if it's sustainable, it also means it's going to be more cost-effective to run during its operational phase. So we're actually making an early investment in sustainable development to ensure that what we have to manage for the next 50 to 100 years on this development is actually more cost-effective in the long run. So lower energy bills, less maintenance, if you like, and so on. We'll reap the benefits in the long term.
Oh, I've lost my hat. Once I had retrieved my hat, I wanted to find out a little bit more about their water recycling plans. Water management and recycling is a major consideration when planning sustainable housing, because at the moment we use completely clean, drinkable water and essentially flush it down the toilet. There's an option to recycle so-called grey water, which is any used water that hasn't been down the loo with all the associated extras. We could use this for things like flushing the toilet or watering plants, basically anywhere that we don't need to drink it. We headed over to the water management part of the development for Gavin to tell me a little bit more about what they were doing on this site. So at the moment we're here by this very lovely, surprisingly lovely lake actually. What's the lake doing here? What's it part of on this site?
So the lake's part of our water recycling system, but also it has other uses as well. If you like, the whole water attenuation and recycling system we have across the site has many purposes. The lake actually retains water on the site, so as you can imagine, a site of 150 hectares has an awful lot of water falling on it when it rains, and we need to deal with all that water. So what we've done is, by attenuating the water on site, we are alleviating flood risk. That water gets recycled, and there are two water networks across the whole of our site. A normal, not potable water network you get from your normal supplier, so Cambridge Water around this area, and then there is a second network that was used for irrigation, for toilet flushing, and also now for washing machines as well.
So you've got two different kinds of water going on.
Yeah. I think water recycling has been around for many years, hundreds of years, but what we're doing here is doing it collectively, if you like. The whole system is feeding the whole site, so you're not reliant on individuals collecting the water themselves. This is being done centrally, and it's the first time it's been done at this sort of scale. The lake also provides amenity both for the public, people, as you've just said. You quite like the look of the lake. It's a very nice place to be. Hopefully when the sun's out a bit later on in the year it'll be even nicer. But on top of that, it also creates habitat for wildlife too.
And speaking of wildlife, one of the things that I found really surprising on site was the commitment to ensuring that their impact on the local environment was neutral.
So throughout the delivery of the project, we've had to look after great crested newts. So in the area immediately in front of us here, there's a large pond just beyond those bushes there. The small green fences you see are how we control the movement of the newts to ensure that they don't get out into the wider site and get squashed, putting it bluntly. And we're standing at the moment right on top of our Newt tunnel. And this tunnel is of a reasonable size and will allow the little gems to migrate between the ponds and ensure that they don't get hurt in that process.
Well, that's a good Newt story, isn't it, if ever I heard one. Gavin Heapy there, Construction Director for the North West Cambridge development site.
And fresh off the building site, Emma Sackville has come to join us in the studio. Emma, what are the downsides to a project like this?
Well, there are actually a couple. They don't have direct transport links. So the development site is quite far out of the town, which means that if people need to come in and out of town to work and they drive, that increased carbon dioxide output could have a negative effect on the whole building site. As we've heard so far, technology is moving quite quickly in this area as well. So it could be that the things they've already got in place might become out of date. Another potential problem is that they're actually building the site on greenfield land, which could be used for other environmental purposes. And actually, they're finding it fairly difficult to stay on budget because building this kind of thing on this kind of scale is pretty tricky.
So is this the model for future developments then?
Well, it's probably one of them, but it's not the only way to do it. I went to see one other new development in Cambridge, which thinks that communities have a really important role to play in the future of our housing.
So I'm Johnny Anstead. I'm a director of a company called Town, and we're building a development on the site that we're standing on. It's a 42-home co-housing scheme, so it's a housing development with a difference.
What exactly is co-housing? What is this difference?
So co-housing is it's a housing scheme like any other, except that the people who live there tend to know each other. So in this case, they're a group of people who've been kind of friends for the last few years and who together have kind of come together to prepare a plan for how they want their neighbourhood to be. They've been active in shaping the place. They prepared a brief for us before we got involved, which basically said what they wanted the place to be like and feel like and how they wanted it to function and the kind of building standards that they wanted it to achieve. And all of them like the idea of living in a neighbourhood where they know their neighbours and where they can sort of pitch into community life.
And could you tell me a bit more about the community aspect of the co-housing scheme?
Yeah, of course. As well as knowing each other, they also have certain things which are going to really shape the way that the community functions. So there's going to be a thing called a common house, which is basically an extra building where people can eat together if they feel like it, where they can do exercise classes or have meetings. There'll be a really good kitchen. There'll be some laundry facilities. So, for example, if you don't want to have a washing machine in your own home, you can do without one and just use the shared laundry facilities. You don't have to, but it's there for you if you want it to be. It will have a large shared garden at its centre, so pretty much all of the houses and flats will back onto this beautiful kind of green space where kids will be able to play safely, people will be able to grow food, and just generally a great place to sort of socialise.
I hate to say this, it sounds slightly verging on hippie.
Yeah, I think that it does have a sort of hippie streak through it. Of course, it has a hippie ethos in all the good ways. It means that people have, these people tend to be committed to a more communal way of living. It's not a commune, but a more communal way of living. It's they're people who are interested in reducing their environmental impact. So yeah, and I would say it is in a good way a sort of a hippie way of living, but actually in other ways it's very straightforward.
So do you think it's a scalable, feasible model?
Look, this is a 42-home scheme. It's probably at the upper end of the range in terms of the size of co-housing schemes that are generally developed. So it's never going to be something that you can deliver at 1,000 homes at a time. And yet, we're in the middle of a massive housing crisis in the UK, and the stuff that's being delivered by the volume house builders is all kind of of a kind. It's all pretty generic, and everyone knows what the shortcomings are of new homes. They can be box-like. They don't always perform very well. People don't know their neighbours and they're kind of soulless. I think that even if this isn't the answer to the large volume of houses that needs to be built, it definitely is sort of leading the way and kind of showing how a different kind of living can be part of the mix.
Johnny Anstead, Director of Town.
Now, small-scale living does sound great, but as we've heard at the end of that piece, it probably isn't going to be a universal solution.
Agreed, especially given that by 2050, the UN reckons that the majority, that's 70% of us, will be living in cities.
So what can we do to make a so-called sustainable city? Is it even possible? Rachel Cooper from Lancaster University has an opinion. Rachel, is this an oxymoron or is it a reality, a sustainable city?
Well, it's a bit of an unobtainable utopia. I think we can move towards a sustainable city, but actually what we need are places that are livable and that conserve the planet's resources and are adapting to climate change. So sustainable, yes, towards sustainable. There's no such thing as a sustainable city in the end.
Why can't we have a city which is thoroughly good for the environment?
We can have one that's thoroughly good for the environment, but the measurement targets change constantly depending on which scientists are working on it and what's happening to the climate, what's happening to our resources. So it's about working towards those targets, achieving them, and then going beyond it.
What are the hurdles or the big challenges in the way then? What do we need to do?
I think we need to do all the things that you've heard. So we need to adopt the emerging technologies as quickly as possible and introduce them. So we heard about solar panels, new materials, new types of homes, and ensure that planners and designers and architects understand them and know how to use them. We need designers that can be creative with those technologies, adapt them, but also design places that are not just full of technology, but support our well-being. So to design cities that are walkable, that have green spaces, that have places for children to play in. There's lots of dimensions of living in a city. It's not just about density, it's about vitality and intensity. How do we cope with living in those intense, dense places? We have to think about that and design them to support people's well-being.
I'm glad you brought that up, because very often people tend to obsess on how many people we need to pack into a space, and they don't, I think, always consider the soft fascination that engaging with nature brings and the well-being effect and the relaxation effect, which you're not going to get in a city.
Well, you're not unless you design it appropriately. I mean, we know that our well-being is affected by the physical environment, the ambient environment, how much light. If we get noise from our neighbours, it increases our potential for depression. We need these tranquil places in towns and cities that allow us to walk, to cycle, and to get that quiet time that we need to support our own health and well-being.
What about other things that can save energy? Because the one thing that strikes me, I drive around town at night and everywhere is lit up like a Christmas tree.
So this is where the term smart cities come in. Smart cities are all about putting sensors in places, monitoring our use of energy. And so I think the technology eventually will come in there. We will be able to turn lights off if people aren't in the space. We'll be able to understand how people are moving around to support their movements and to reduce the number of cars, so we have the public transport in the right place. So smart city agendas, where we're using technology to monitor systems, will help us reduce the use of those systems when they're not needed.
You bring up the issue of traffic. Now, that's great. If you're building a new city from scratch, then you can plan it so it's fit for purpose. Horrible phrase, but for the 21st century, with the sorts of vehicles that need to move in mind, the scale of those vehicles, the densities of those vehicles. Most cities that are worth living in, though, they were built hundreds of years ago, certainly in Britain, and they're not retrofittable like that.
Well, we're attempting to do that, and if you talk to people in London, you will see as many cycleways being implemented, and that may help, as well as regulation and policies about where you can use cars, how you can support other ways of transport. We've really got to rethink cities. We've got to look at cities that have no car policies. You know, like we're doing some work on No Car Birmingham, trying to imagine what you'd have to do to create a city without cars in its centre.
But why are you declaring war on cars? What's wrong with cars?
We're not declaring war on cars.
Sounds
we have to either. No. We're just trying to imagine what future cities might be like in terms of reducing the number of cars or other types of transport to enable people to be as mobile as they want to be. And so we have to use our imagination, particularly with these cities that, as you say, have been here for hundreds of years and have roads and transport connections which have been there for a long time. We have to really be creative about how we think about those places.
Lastly, Rachel, why is there this prediction that everyone's going to head for the city?
I think it's employment. If you look at the way students have been moving from where they do their undergraduate degrees in the north of England, they all go south at the moment. They all go to London. So we also have to think about policy, legislation to support people living in cities. And the reason they go there is because that's where their employment is.
Rachel, thank you. That was Rachel Cooper from Lancaster University. Thank you also to our other guest this week, Darshil Shah.
And finally, it's time for Question of the Week. Fanny Yoon has been keeping her ears peeled for the answer to Mark's question.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
How do active noise cancelling headphones work? If they play back loud ambient noise, could they be as dangerous as listening to loud noises?
Thanks, Mark. I called up Dr. Trevor Cox, professor in acoustic engineering at the University of Salford, to cut the rumble on this question.
Well, normal ear defenders that you might wear to protect yourself from damage from noise normally just have a sort of cup which gets in the way, sort of physically blocks sound getting from the outside world into your ear canal. But what active noise control headphones do is they actually use electronics. So they have a little microphone on the outside that picks up the noise you don't want. And on the inside of the cup, they've got a little loud speaker which plays the inverse of the sound, and that cancels out the noise. And I can give you an example here. I've taken a recording of the International Space Station, and I've shown you what it might sound like inside active noise control headphones. So what will happen is you'll first of all hear this noise, which is all the kind of machinery going on, and then I fade in the inverse of that noise on top of the original, and you'll hear how it cancels out the original sound and virtually gets rid of it. How the active noise control headphones remove the sound is by a process of interference. So you can imagine a sound wave, often see them as a sort of squiggling sine wave, sort of a series of peaks and troughs. Just think of, say, the ripples on top of a pond where you've got peaks and you've got troughs across the pond. What happens is you've got that original noise, and that's got this sort of wavy pattern, and then you've got the inverse of it. Literally imagine flipping it over so that where there was a peak in the original, there's a trough in this new sound that you're trying to produce to cancel things out. And when you add a sort of peak to a trough, you get nothing because they cancel each other out. And it does that through the whole sound, and that's how it removes the noise and cancels it.
So if you play two noises, it's going to be twice as loud. But if you play one sound and then invert it so that the peaks and the troughs cancel each other out, then you get no noise at all, and you won't hurt your ears?
Well, yes. I mean, imagine if you were just in your kitchen, you put a kettle on and you put another kettle on. It's obviously just going to get louder. That's because all the peaks and troughs are randomly arranged. When one kettle's making sound, there's no relationship to what's going on in the other kettle. But if I was to take a recording of the first kettle and to invert it, so to flip around the peaks and the troughs and play it out of a loudspeaker next to the kettle, then these peaks and troughs would exactly align, and you would get, well, if you could do it properly, you get nothing. Of course, with active noise control headphones, there's a little bit left over because nothing's perfect.
Big thanks to Professor Trevor Cox from the University of Salford. Next time, we're going to untangle our tentacles with this question from Android.
I've heard the octopus are colourblind. So, how can they so reliably match their background colours when they camouflage themselves?
If anyone has any hidden thoughts about this one, then you can email chris@thenakedscientist.com. Find us on Facebook, tweet @nakedscientists, or join in the debate on the forum, thenakedscientist.com/forum.
And that is it for this week. Thank you very much to Emma Sackville for putting the programme together. Next week, we'll be getting our heart rates up because we'll have a special programme from the British Heart Foundation's conference in Manchester. If you have any questions relevant to heart disease, you can send them in now to chris@thenakedscientist.com. The Naked Scientist comes to you from Cambridge University. It's supported by Rolls-Royce, the STFC and the EPSRC. I'm Chris Smith, and until next time, goodbye.